Hello, welcome to everyone in this video. This is lecture number 18 on solid state physics. Today we want to discuss about the superconductivity. In this part we will discuss the experimental result, then critical temperature, then critical magnetic field, then Meissner effect, type 1, type 2 semiconductor, then London equation, then penetration depth and isotope effect. All these things will be discussed in this lecture series. You can see this is the syllabus: crystal structure, elementary lattice dynamics, magnetic properties of matter, dielectric properties of material, then Drude's theory, elemental band theory. All these 6 parts already covered in previous lecture. Today we want to complete this superconductivity, and with this video this portion, that is the total syllabus of this portion, will be covered up, right? So if you want to watch previous lecture, you can go to the description box. There is a link of the playlist of this solid state physics for UG. So let's start superconductivity. Actually, the phenomena, you know that when within a conductor, the free electrons is the main elements to conduct current within this metal. When you increase the temperature of this metal, what happen? Then the kinetic energy of this electron will be increased. When you apply the temperature or heat within this metal, then what happen? The kinetic energy of the electron will be increased, and due to increasing kinetic energy, its speed will be increased, its velocity will be increased, and high speed electron makes more collision with the ions and between electrons also. So there is a probability that the increase the collision probability will be increased, and due to collision the electron makes more resistive, that is resistance of this conductor will be increased, that means conductivity will be reduced. So with increasing temperature, the conductivity of the material of the metal is decreased. In the semiconductor, you know, with increasing temperature the electron hole pair generation will be increased, which is the cause of the increasing of conductivity. But in case of metal, there is huge number of free electron, that's why the collision will be increased, and that collision makes you the resistivity increase, that is the conductivity is reduced. In the opposite sense, if you reduce the temperature, then conductivity will be increases or resistivity will be decreases. So with decreasing temperature, resistivity will be decreased. So this curve will be like that. So this is a theoretical part, this will be the theoretical part, that is we reduce the temperature, will be reduced. But in experimental result, what happened? After a certain value of lowering value of the temperature, it does not follow this phenomena. Up to this temperature, that is 4.2 Kelvin, it's follow up, but it does not follow that path. It does follow this sharp change, that is at this temperature the resistivity will be sharply go to the zero, that means resistivity becomes zero. So there is an anomaly with the experimental to theoretical result. So this is the first time where the experimental result says there is some mistake or mismatch, or there is some new physics. So this is the experimental result where first time observed that there is a zero resistivity, and the experiment with the different metal, you can see for Hg this is 4.2, for Pb lead 7.25, cobalt, and this is a composition YbA2Cu2O7 90 Kelvin, H2S 203 Kelvin. So this is the experimental result. You can ask me that how we can reach this type of temperature. This type of temperature you can reach by, you know, for ice 273.15 Kelvin, for dry ice 194.64 Kelvin, for liquid nitrogen 77.15 Kelvin, for liquid hydrogen, sorry, liquid helium, this is helium, for liquid helium 4.04 Kelvin. So using liquid helium you can reach this temperature, no problem. Okay. So the temperature below which the normal metal converted into superconductor is known as the critical temperature. So the critical temperature is that temperature below which the normal metal behaves like a superconductor. Superconductor means zero resistivity. There is no resistance. So below the critical temperature you make superconductor, no problem. This superconductor can be converted into the general metal or simply conductor. This superconductor can be converted into the simply conductor by three process. How? Increasing the temperature above the critical temperature is behaves like a normal metal. You can also introduce magnetic field. If you introduce external magnetic field, then also superconductor change into normal metal within the critical temperature region also. That's mean its temperature is below critical temperature, but the external magnetic field causes superconductor converted into normal metal. Another thing is the high current density. When you passes through the current on the superconductor, after a huge after a value, a large value, this superconductor becomes normal conductor. So there is three phenomena which can destroy the superconductor or which can convert the superconductor to the normal metal. These three things is the temperature, magnetic field, external magnetic field, and the current density. So within a same graph representation in three dimension, you can take one axis temperature, one axis current density, one axis external magnetic field. Above the temperature Tc, this is become normal, that is critical temperature. Above the current density, this become normal, critical current density. Above this magnetic field, this become normal metal, critical magnetic field. So within these three critical region, this is the superconducting state, and above this region or outside to this region, this is the normal state. So in a simple representation you can discover or distinguish between normal metal to superconducting metal. So Jc is the critical current density, Bc is the external critical external magnetic. Now if you wants to know about the relation of the critical magnetic field, like that. So this is critical magnetic field at temperature T, which is equal to critical magnetic field at 0 Kelvin with the 1 minus T minus T square. Okay. So this is the relation between critical magnetic field at temperature T with critical magnetic field at 0 Kelvin. Next thing is the Meissner effect, very important phenomena for the superconducting material. It was observed in 1933. That is, the material is diamagnetic. Superconducting material is diamagnetic. How? That is, if superconducting material is diamagnetic, B is 0. So you know B equal to mu naught H plus M. H is the external field and M is the magnetization. So M equal to minus H, and you know M equals to chi H. So chi equal to minus 1. Chi is nothing but susceptibility. So you can confirm that the susceptibility of superconducting material or superconductor is minus 1. So minus 1 dielectric means this is minus 1 susceptibility, means this is diamagnetic material. That's why the superconductor is diamagnetic material. Here is a simply an experiment, that is this is for ideal conductor and this is for superconductor. For ideal conductor, above T greater than Tc, this is magnetic field passes through the material. For superconductor, also above the critical temperature, magnetic field passes through the material. But below the temperature, below the critical temperature, in ideal conductor, the magnetic field passes through the material as before. That means above critical temperature and below critical temperature, these two phenomena, that is the magnetic field passes to the material, is the same. But in case of the superconductor, you can see that is below the critical temperature, the magnetic lines of force cannot passes through the material, it passes outside the material. Okay, so it behaves like a diamagnet. So this is the difference between ideal conductor to superconductor. So simply this experiment, using this experiment, you can confirm whether this material becomes superconductor or not. All the metal cannot be superconductor. the metal can superconductor if it behaves like this type of phenomena. Below a certain temperature called critical temperature, this superconductor become diamagnetic, but above this temperature it does not diamagnetic. That's the basic difference between superconductor to ideal conductor. And this experiment also confirmed that is the superconductor is diamagnetic material because its lines of force cannot passes through this material. Next important thing is the type of superconductor. That's mean when a material or the metal is m equals to minus chi, this is the superconductor. Above the critical value, this become normal conductor, right? So if you increasing the external magnetic field, superconductor becomes a normal metal. This is known as critical magnetic field. Okay, if the graph representation will be like that, so this is called type 1 or soft type superconductor. But in some superconductor, this transition is not sharp. This is like that. So there is a two critical magnetic field, lower critical magnetic field, higher critical magnetic field. This is known as tier 2 or hard. So it's changed from superconductor to normal conductor in a sharply, but it's changed in a delay. So this is normal state, this is superconducting state. Between these two states known as vortex state. So vortex state is nothing but the mixture or the mixing state of the superconductor and normal conductor. Okay. Since it cannot transit from superconductor to normal conductor sharply, that's why this is called hard, because it cannot flick from superconductor to normal conductor with a just change in the magnetic field in certain manner. Okay, so this is soft type 1, this is hard type 2. There are different some difference also. This type 1 shows Meissner effect. That is Meissner effect, you know, this below the critical temperature it's behave diamagnetic, above the critical temperature it's a paramagnetic, but it does not show completely Meissner effect because there is a transition. And current flow to the surface only in case of soft superconductor, current flow through the surface only, but in case of the type 2 superconductor, that is hard superconductor, current flow through the material also. That means current flow on the surface as well as current flow go through the material. That is, there is a penetration of the uh, carriers. That is electron here also, because in metal there is no hole represent. And current flow surface only. Example, aluminum, mercury, lead is the type 1 soft, and titanium, and this composition is hard. So this is the basic difference between two types of superconductor, type 1 soft, type 2 hard. Next is the vortex stage, is nothing but type 2 superconductor material where two states, that is the superconducting state and the normal state, are superimposed, or the complicated state between these two, mixture of these two states, the vortex state. Next important things is the London equation. Actually this equation gives you the mathematical explanation of the superconductor. The mathematical explanation of the superconductor can be found out from the London equation. Theoretical explanation is the London equation. And 1935, F. London and H. London are established these things. According to their theory, there exist two types of electron. According to their theory, there is normal electron and super electron. And super electron actually is the main cause of the superconductor. That is, high current rate, zero resistivity is the cause of the superconductor. Okay. If you consider Ns is the number density of superconductor within the superconductor, the number density, you know, number per super electron per unit volume. Density means divided by 1. So force on a electron, you know, charge into electric field. Force is nothing but mass into acceleration. So acceleration is like that. and ddt of Vs. Vs is the velocity of the superconductor. How you will get this Vs? You know IL equal to JV. is current, J is length, J is current, volume current density, and what? This is volume. So J equal to I by A. I equals to Q by T, and A is nothing but volume by length. So L by T is V. Small v is velocity, capital V is volume. And Q by V is nothing but the Q is N into E, number into electronic charge, and volume. So N by V is the small n, that is the number density. So J equal to N E V, small n V, S for superconductor. So Vs is nothing but 1 by Ns is J. So put this value here, and derivative only Js, because these two are constant. So you will be get this relation, and this is London first equation. dJs by dt equal to ns square by m e vector. J is the superconductor current density, ns is the uh, density, number density of the superconductor electron, m is the mass, e is the electronic charge, and capital E is the electric field. For normal conductor, you know J equals to sigma E. So if E equals to 0, J equals to 0. But in superconductor, if E equals to 0, you can see E equals to 0 means dJs by dt equal to 0. That is Js is constant. So you can see mathematically that without any electric field, that means no voltage, normal metal have zero current, but in case of superconductor with zero electric field, that is no voltage apply, then current density is constant. That means constant current flow through this superconductor. That is the beauty of superconductor. That is the basic difference between superconductor to metal. That is, when a metal becomes superconductor without any external field, without any external voltage, current flow through within the material, within the superconductor. Okay. So these are the explained from this mathematical, that is the London first equation. Go to the London second equation, like that. From first equation, this is raised, so E equals to like that. You know Maxwell third equation, curl of E equals to minus del B del T. Put this value of E here, and taking this curl into account, so this is curl of J's. Integration and dt is cancelled, and this integration B minus B0. So Meissner effect, that is the internal magnetic field, that is at 0. This is 0. So finally you obtain this expression, curl of J is equal to this. So this is the London second equation. What is the conclusion of second equation? You can see curl of J is equal to like that. If you taking this curl of this one, you will be get this one, and this curl of B, you know, mu naught J, mu naught epsilon daily del T. So mu naught J and this one. So you just write down here. Here you know that is the current density is 0. This portion is 0, so only this is present. No. Sorry. For E equals to 0, without external field, electric field, that is voltage is 0. For this is 0, will be present only this term and that term. This term is 0, and this is the vector identity put here, and divergence of J is 0. So finally you obtain this expression. In this expression, this is known as the penetration depth. Lambda L is the root under m by ns square by mu naught is penetration depth. And mes is not rest mass, m is the effective mass. Actually mass will be changed within this superconducting state of the electron. Superconducting electron mass will be changed. This is the effective mass. Okay, you just I just wants to write down these things here. That is, this is not a normal mass, this is the effective mass. You know effective mass very well. Effective mass and other things, you know, this is the density, this is the electronic charge, this is the constant, that is 4 pi 10 to the power minus 7 Henry meter. Go to the next portion, and this is the representation of like that with this distance. Okay. This is the current density. Js is the current density, and this is the magnetic field. Now, from another important things, the second London's equation gives you this relation, and you know the magnetic field is curl of A. A is the vector potential. So if you compare, J can be written as in terms of vector potential. Current density due to superconducting electron is like that. Next important thing is the isotopic effect. Isotopic effects mean, you know, there in the metal there is various isotopes, and these isotopes mass is different. So the critical temperature is depends on the isotopes. That means with changing the mass of this material, that is with the isotope, different isotope, the critical temperature also different. For different isotope, the critical temperature also different. For example, Hg, mercury, alpha is like that. For mass 199 point, this one. For 203 point, this one. Alpha is the constant. For different metal, this will be different. Okay. Next, there is a problem which asked in 2021, I think. Given here, the London penetration depth 14 is given like that, and atomic weight will be 118.7 U, and Tc critical temperature 3.7 Kelvin, effective mass of electron 1.9 Me. Me is the rest mass of electron. So penetration depth formula, you know, M is written here 1.9 into 9.1 to 31 kg. Ns is the density. Density can be find out N by V. So Na M by V M, and this is nothing but M by V is rho, and this is M. So put this value Na is the Avogadro's number, rho is the density which is given 7300 kg per meter cube, and M is the mass of this tin. What is the mass? Mass is nothing but this 118 point U. U can be converted into the kg by multiplying 391 MeV. And what is MeV? Mega means 10 to the power 6, and EV to joule you need to multiply by electronic charge, that is 1.6 10 to the minus 90. So I think you can do this calculation. After calculating, you will be obtain these types of value. Putting this value here is the, I just cross this thing. This is not, just put this value in the right manner. You will be obtain. The final result will be 0.147 angstrom. Okay. I think you can do this calculation. You just remember the density, number density will be, you need to find out from this given data. Okay. Next important thing is the BCS theory. BCS actually three scientists, Barden, Cooper, sorry for BCS. In 1972, they got Nobel Prize to explaining the superconducting state. Actually, London equation cannot explain all the superconducting phenomena. All the phenomena of the superconductor cannot be explained by London equation. This was actually explained by BCS theory. This theory actually based on two things. One is the electron phonon electron interaction, another is Cooper pair. Actually here lattice vibration, when the lattice is vibrated, there is phonon emission. This is the important part. How? Just think. This is a superconducting state. That means atoms are arranged in regular way. That's why there is no resistance. Electron can pass through like that. There is no resistance. There is no lattice vibration. So current flow is very much high. That's why this is superconductor, resistivity is 0. But what happens when electron moving to this region, superconductor, in certain region electron are trapped. How? There are all positive signs. There are all positive ions, and this is electron, so they are attracted. So they make distortion in lattice. That means it's make vibrate. There is no thermal agitation, no thermal vibration, but due to distortion of the presence of the electron, when this electron move and this is trapped, these ions are attracted, and this make distortion of lattice, imperfection of lattice. This make phonon emission, not photon. Make it phonon. Phonon means lattice vibration. Phonon emitted. Then what happen? There is a cloud of positive. There is a cloud of positive region, and these positive regions attract another electron. So like that, these two electron makes a pair. These two electron makes a pair. So here two interaction happen: electron repulsion, Coulomb repulsion, and electron phonon. This phonon makes attraction. So there is two interaction: electron Coulomb repulsion and the electron phonon attraction. This attractive part is much greater than the repulsion part. That's why they makes a attraction. And you can see these two electron make a pair. These two electron make a pair. These two electron make a pair, and this pair known as Cooper pair. Okay. So you think what happened? This electron passes through air, they make a positive region, and this positive region, this phonon gives you attraction of another electron. So there is two interaction: electron repulsion and electron phonon attraction. Electron phonon attraction is higher than the electron repulsion. That's why they make pair, and this pair known as Cooper pair. Okay, this Cooper pair actually interact by phonon. Phonon is lattice vibration. Now if you the incident wave function, this is an ejected wave function, this is so when two electron within superconductor interact to each other by phonon, they make Cooper pair. So the binding energy of the Cooper pair 10 to the minus 3 electron volt, very small. Total spin of Cooper pair is 0. Behaves like a boson. This makes a boson. And follow the Bose-Einstein statistics. If T greater than Tc, Cooper pair. So these Cooper pair actually present in superconducting state. When the temperature is above critical temperature, that's mean superconductor change to normal metal. Then Cooper pair also disappear. So Cooper pair present in this superconducting state. So I think clear about the BCS theory, which says how these superconducting material make a pair, Cooper pair, and how they interact with the phonon, etc. etc. I think you clear about all this. This is a previous year question. You need to solve this question. If there is any problem to solve, you can see there is another playlist for solution of previous year question also. So I think clear. If there is any doubt, you must comment in the comment box. This is all about me, and this is my contact detail. You can connect with this Telegram channel, and this is my YouTube channel details. Go to this channel, you will get different field related videos on mathematics. Like this session if you learn something from this session. Share this video to your friends, either he or she also get benefit from this video. Subscribe this channel if you new in this channel. Those already subscribed, thanks for subscription. Press the bell icon to get notification of upcoming videos. So take care. We'll meet in the next video as soon as possible. Thank you.